In this video, we are going to be learning about shear and moment diagrams. Sometimes you'll see them referred to as V and M diagrams. The V is often associated with shear, and M is always associated with moment. So let's first start off by talking about what are shear and moment diagrams. Shear and moment diagrams graph the change in shear or moment over the length of a beam. So just as we learned in our last video that beams have internal forces associated with them. So if we had some loading on this beam here, we know that the shear and the moment are going to change as we move through this beam, depending on if we were to cut it here or here. The shear and moment are going to be different there at those different points. But if we develop a graph or a diagram of the shear and moment, we no longer need to cut it multiple times to find our internal forces at various points. We can just develop this graph or diagram, and we can just pull values from this graph or diagram, which saves us time and energy and is way more efficient than cutting the beam, say, in 10 different places. If this beam was 10 feet long and you needed to know the shear at 1 foot lengths, just using the knowledge from the previous video, you would have to cut this beam 10 different times in order to achieve that. However, if we develop a shear and moment diagram, then we can just pull those values off that diagram. And it takes about 1/10 of the time. So there are two different ways you can draw a shear and moment diagram. The first way is going to be to graph shear and moment equations. So you can develop equations for these different graphs and then just graph those lines. Or you can also draw a shear and moment diagram by visual inspection. However, both of these ways start the exact same way. As per all of our problems in statics, our first step is always going to be to draw your free body diagram. And then you're going to write your equations of equilibrium and solve for your reactions. Then once you do this, then you can decide which method you want to use to draw your shear and moment diagrams. In this video, we're going to go over an example of both ways. So let's go ahead and start with our first example. In this example, we're going to use the graph equations method. So let's, for this example, use a fixed beam. because we haven't seen one of those in a while. And let's just say that it's got a uniform distributed load acting on the first part of it, and then there's a point load acting down here. Let's go ahead and give dimensions for this thing. Let's say this is 5 feet, this is 2 feet, this is 2 feet. We'll go ahead and say this point load is 10 pounds, and the uniform distributed load is going to be 2 PLF. And then, of course, we'll label this end down here A and this end B. And we're just going to want to draw the shear and moment diagrams. So like I said, the first thing you're going to want to do is draw your free body diagram. So for this example, again, you just start by drawing your object, apply your forces, and apply your reactions. In this case, because it's fixed, we're going to have a reaction in the X, reaction in the Y, and we're going to have a resisting moment. Now you can use your equations of equilibrium to solve for your reactions. I already solved for the reactions previously. If you don't know how to solve for these reactions, go ahead and head back to our equilibrium of a rigid body video, and there it will explain to you how to find reactions. But for now, I'm just going to give those to you because I already solved for them. So MA is going to be equal to 95 pound-feet. Going counterclockwise. AY equals 20 pounds acting up. And AX equals 0 pounds. Again, if you don't know how I solved for those, head back to our equilibrium of a rigid body video to learn how to solve for those reactions. Okay, so once you've drawn your free body diagram, you solve for your reactions. The next step, step number 3, is going to be identify your number of equations. When you're drawing a shear and moment diagram, your shear and moment equations are going to change anywhere along your beam where the loading changes. So in this example, our equations for shear and moment are going to change here and here. So the beam is split up into 1, 2, 3 different sections. So there's going to be 3 different sets of shear and moment equations. Again, anywhere where the loading changes, your equations for shear and moment are going to change. So we're going to have a set of equations for x between 0 feet and 5 feet, x between 5 feet and 7 feet. And then finally, our last set of equations is going to be for when x is between 7 feet and 9 feet. So now that we have the number of equations and what those are going to be identified, we can go ahead and start solving for our shear and moment equations. So step 4, determine shear and moment equations. So we're going to start with when x is between 0 and 5 feet. Now this distance x refers to where we're going to be cutting our beam. At what point of the beam are we trying to find the shear and moment? So between if we start at the left end of the beam and say that x equals 0, x is going to increase as we move to the right. So for this first set of equations, we're going to cut it at a distance x somewhere between 0 and 5 feet. So somewhere in this distributed load area, we're going to cut it, and we're going to cut it at a distance x. So again, we're going to have our beam. We're going to cut it at a distance x. And we're going to draw a free body diagram of this cut portion. So we've drawn our cut portion. Now we need to apply our loads. Apply our reactions. And as we always do with cut sections, we apply our internal forces. We're not going to apply our normal force because in this case, we're just looking for diagrams for shear and moment. They're not asking for a normal force diagram, although you could graph that as well. But in this case, we're not being asked for it, so we're not going to worry about it. Also, remember to apply your internal forces in the positive direction. If you can't remember how to determine what positive means, head back to our internal forces video, and it goes into great depth there and detail how to determine what positive is. So now that we've got our free body diagram for our section being cut at a distance x between 0 and 5 feet, we can go ahead and use our equations of equilibrium to solve for V and M. So we're just going to go ahead and start with our sum of forces y equals 0. I'm going to select up as positive. Again, this is just the same thing we did in our last video, in the internal forces video, where we're just solving for V and M. So sum of forces y, we're going to get 20 pounds minus 2 PLF times, you might be tempted here to put 5 feet, but remember we're cutting the beam at a distance x, So this is really times x. This length here, we're just looking at this cut section, cut at a distance x. So the length of this rectangle from the distributed load is going to be x. So that's why we put x here. And then minus v equals 0. Then we can go ahead and solve for v, and we get that that's negative 2x plus 20. So that's our equation for shear for this first part of the beam. For the beam that lies between 0 and 5 feet. That's our equation for shear. Now we can do our sum of moments equation. Again, I always like to take the sum of moments about the cut surface. So about x equals 0, pick a direction as positive. So we're gonna get 20 pounds times, again, a distance x minus 2 PLF times x times our moment arm, which is going to be x over 2. Minus m. And of course, don't forget your reaction moment, which is 95 pound-feet, which equals 0. So we can solve for m, and we get that m equals negative x squared plus 20x minus 95. And that's our equation for moment. So now we can go ahead and move on to our next section. So for x being between 5 feet and 7 feet. So if we just redraw our beam to remind ourselves what it looks like. We're gonna be looking at this section here, that part of the beam. So we need to cut the beam somewhere in that section. And again, that there is gonna be our distance x. Now for this one, I'm going to look at the right side of the beam rather than the left side of the beam, because when I look at it, I can see that the right side of the beam has less forces, so it's probably going to be a little bit simpler to calculate and work with. So I'm going to go ahead and draw a free body diagram of that cut section. And I'm going to get 10 pounds here. So free body diagram, draw your cut section, apply your forces, apply your reactions, and now apply your internal forces. Again, we're not going to worry about our normal force because this problem is not asking for it. And again, apply your internal forces in the positive direction. And then, of course, add your dimensions. So we know this is going to be 2 feet. Now, this dimension here gets a little bit tricky. So if we draw a picture of the whole beam over here, and this is our cut section here, and we've got that force there, we've got our uniform distributed load here. So remember, we're cutting the beam at this distance x here. We know this dimension here is 2 feet, and we're trying to find that dimension there. But we also know that the full length of the beam is 9 feet. So we can go ahead and say that this mystery dimension here is going to be the total length of the beam minus 2 feet minus x. And that will get us this length here. Because you've got this full length, and then you are subtracting out 2 feet, subtracting out this x, and you are left with this portion here, which is that length that we were looking for. So that length there is going to be 7 minus x. Apply that to our free body diagram. And again, we can just use our equations of equilibrium and solve for our shear and moment equations. So sum of forces y equals 0. Choose a direction as being positive. And we're going to get v minus 10 equals 0. So v equals 10. Sum of moments about x equals 0. Choose a direction. So we're going to get m plus 10 times our moment arm, which in this case is going to be 7 minus x, equals 0. We can solve for m. And that's going to be our moment equation. So we're done with our middle section of the beam now, and we can go ahead and move on to find equations for x being between 7 feet and 9 feet. Again, if we just quickly redraw our beam to remind ourselves what we're working with. We're looking at this portion of the beam down here, so we're going to cut it somewhere in that section. And of course, that distance there is going to be our distance x. Again, I'm going to look at the right side of the cut section. Apply our forces. There are no forces on that side. So apply our reactions. There are no reactions. Apply your internal forces. Go ahead and do that. All right, and then you can use your equations of equilibrium to determine that v equals 0 and m equals 0. All right, so now that we've got that, we can go ahead and draw our shear and moment diagrams. So let's go ahead. We'll start with shear. And just to remind ourselves, I'm going to go ahead and write out our piecewise function of shear that we developed. So v of x is going to equal I have 2x plus 20 for between 0 and 5 feet. It's going to equal 10 for x being between 5 and 7 feet. And then it's going to be 0 between 7 and 9 feet. So we can simply just graph these. And just to remind ourselves, we're working in pounds. So we look at this between 0 and 5 feet. We use this first equation of negative 2x plus 20. So we know that that's going to be a negative sloping linear line with a y-intercept of 20. So we know 20 is going to be there at 0, and we can plug 5 into that equation. So negative 2 times 5 plus 20, and we're going to end up with 10 over here at 5. And that's a linear line. All right, then between 5 and 7, it stays at 10. And then between 7 and 9, it's 0. And it's really as simple as that. You just graph those equations that you found. So we can go ahead now and look at our moment. I'm going to write out our piecewise function for that. So we're going to have negative x squared plus 20x minus 95 between 0 and 5. And we're going to have 10x minus 70 between 5 and 7, and 0 between 7 and 9. And then we just come over and we graph that piecewise function. Again, just reminding ourselves we're working in pound-feet for a moment. So for this first equation, if we were to plug 0 into that equation, we're going to get negative 95 as our y-intercept. And if we plug 5 into that equation, going to get negative 20. And it's a negative x squared function. Now moving on to our next one, if we plug 7 into that equation, we get 0. So that's going to go up to 0. And that's going to be a positive linear line. And then it stays at 0. And those are your shear and moment diagrams. It's really as simple as just graphing those equations that we found up above here. So that's one method for drawing your shear and moment diagrams. The other method is going to be by visual inspection, and we're going to use example number 2 to demonstrate that. So for this example, we're going to pick a beam that has a little bit more complicated of a loading on it. That way you can just see all the different things that occur when you're just looking at something and trying to develop the shear moment diagrams by looking at it. Hopefully give you a little bit more exposure to different things that occur. This is not drawn to scale, but that's okay. As long as we label everything, right? And add our dimensions. Boom, boom, boom. We're gonna get 5 feet here, 2 feet here, 2 feet here, 2 feet here, and 4 feet there. Again, this isn't to scale, but you get the idea. Okay, so as I said before, the first thing you're always going to do with these problems is draw a free body diagram and then use your equations of equilibrium to solve for your reactions. So the free body diagram, in this case, you start by drawing your object, apply your external forces, apply your reactions, we'll label all these different points, A, B, C, D, E, F. So this is going to be AY, AX, and FY. So there's your free body diagram. So you're going to use your equations of equilibrium to solve for your reactions. You can go ahead and do that now on your own. I already did it previously, so I'm just going to go ahead and write down what I solved for. If you're having issues solving for these reactions, you can go back to our video on equilibrium of a rigid body, and it will go ahead and explain how to do that in detail. I calculated AY equals 19.7 pounds up, and FY equals 8.3 pounds up, and AX equals 0 pounds, of course. Again, I solved for those previously. If you're having issues solving for those reactions, head back to our equilibrium of a rigid body video, and it'll explain how to do that in detail. So for this, we're going to go ahead and just start drawing our shear and moment diagrams, because we're just going to do it visually, so we don't need to solve for anything else. So this is going to be our shear, and we're using pounds. So when you're doing it visually, you start at the left side of the beam, and you just work your way to the right. So we're going to start by looking here, and then move our way that way. So the first thing we hit on the beam for shear is AY. Remember that shear acts perpendicular to your member or parallel to your cut surface. So for shear on this beam, the first thing we run into is AY, and it's acting up. So we're going to go ahead and bump our shear diagram up to whatever that reaction is, which is 19.7. Again, that's our AY value, and that's where our shear diagram is going to start. As we move right on the beam, we run into this uniform load right there. And so all we're going to do is take the area of that shape, and we're going to bump our shear down by that amount over the distance that our uniform load covers. So the area of that rectangle is going to be 2 PLF for our height times our base, which is 5 feet. So that's going to equal 10 pounds. So our shear has to move down 10 pounds by the time it gets over to this 5 feet right here. So I'll just carry that down. And when I subtract 10 pounds from where we're at, we get 9.7. So we know that that point there is going to be 9.7. Now, when we move from our beam loading to our shear diagram, we're going to increase our X value by 1 power. So in this case, we have a constant load right here. So we have an X to the 0 power up here, which just translate to 1, right? We don't have an X for this line right here. So when we move down to our shear, we increase the power by 1. So we need to have an X to the 1 power. And again, this is going down, so we're just going to have a negative linear line to that 9.7 right there. So then we can continue to move across the beam, and there's no shear, no shear, no shear, boom, until we hit this 10-pound point load right there. Then all of a sudden, boom, we hit shear again, and it's going to bump us down 10 pounds. Just like that. So 9.7 minus 10, you're going to get a negative 0.3. And then there's no shear until we hit this triangular uniform load right here. And again, we're just going to take the area of this triangle, and that's how much shear is going to be applied over that length right there. So the area of a triangle is 1/2 base, which is 4 feet, times height, which is 4 PLF, which is going to be 8 pounds. So this needs to go down 8 pounds before it hits the end of the beam. So we can go ahead and take that 8 pounds, add it to that 0.3, and this is going to be negative 8.3 pounds. Now to connect these 2 points, we see that this is a positive x to the 1 type line. It is linear. So to get from your loading to your shear, we've got to increase the power on x by 1. So this is going to be an x squared. Now, you also change the sign when you're moving down. So this here is going to be negative. So you're going to have a negative x squared type line to finish that off. And then, of course, we hit Fy, and we get bumped up 8.3 pounds back to 0. When you have a simply supported beam, you should always start and end at 0. All right, so now we can go ahead and move on to our moment diagram. See how much faster that was? It's incredible when you can just look at it and figure it out. However, sometimes it does take a little bit of time to be able to develop the skills to just look at it and figure out what it's going to look like. So I would encourage you to write out the equations for your shear and your moment as long as it takes until you start developing that sense for how to develop these shear and moment diagrams without the equations. So to get from shear to moment, we're just going to take the area under the curve of the shear to get to the moment. All right, so I'm just going to split these up into different sections. Now, since we're looking at moment, we're going to have to include this concentrated moment acting on the beam right there. That didn't affect our shear because it was just a moment. So we can go ahead and split these in different sections. And I'm just going to calculate the areas of these sections right here. So when I calculate those, I'm going to get 25, 48.6, 19.4, 19.4, 0.6, 1.16, and this one right here is going to be 10.67. This here, remember, is a second order. So a fun trick, if you didn't know this already, the area of under the curve of a second order is just going to be 1/3 base times height. And that's how you're going to get that there. So once you calculate all those areas, we can just start throwing these onto our moment diagram. So between here and here, the moment is going to change by this combined amount, which ends up being 73.6. And that is going to be positive because the area is above this axis of the shear. It's on the positive side. So this here is positive. And then between here and here, it's going to change by 19.4. Again, that's positive. Same with here. But remember, in here we've got our, between these 19.4, we have our concentrated moment. So it's going to bump it down 100. And the reason it's down is because this is going counterclockwise. If it's going clockwise, it'll bump it up. But this is going counterclockwise, so it bumps us down 100. And then between here and here, it's going to be a negative 0.6 change in moment. Negative because it's below this axis here. And then between here and here, it's going to be this combined value here, which ends up being 11.8. And that's going to be negative. So we have no moment reaction on the left end of the beam, so it's going to start at 0. And then we've got to go up to 73.6. And then we're going to add 19.4 to that 73.6. And we're going to get 93. Subtract 100. Remember, because that concentrated moment bumps us down. So we're going to get negative 7. And then we've got to add 19.4 to that. So we're going to get 12.4. And then we've got to subtract 0.6. Which is going to be 11.8. And then we subtract 11.8, which will take us back to 0. So now we've just got to combine all of these dots. Again, when you move from shear to moment, it's similar to when we moved from the loading to the shear. We're just going to increase x by 1 power. So if we look at this first section, we have a negative linear line. So that would be like having a negative x. So down on our moment, we've got to have negative x squared. So that's going to look like that. Again, I just like to label these second order, because when you start drawing these really small, your second, third, and fourth order start looking the same. So it's just nice to identify what's what. So from here to here, it looks like we've got just a constant line. It's on the positive side, so that's like having just 1, so increase the power of x by 1. We're just going to end up with x. So positive x, so just a straight line between those 2 points. Again, don't forget we got bumped down by our concentrated moment all the way down to -7. So that's just a vertical line. And then to get from -7 to our 12.4, again, we just have that positive linear line. If I would have drawn this to scale, these here should be parallel. But again, not good at drawing to scale. Okay, and then to get from 12.4 to 11.8, we've got a negative 0.3x to the 0. So again, we need it to be a negative x to the 1 to get to there. So it's just a negative linear line. And then this one is where it gets fun. To get to 11.8 to 0, up here we have a second order. So on our moment diagram, we have to increase by the power of 1. So we're going to have a third order. And again, it's going to be negative. And like I was saying before, those start to look all the same. So I just like to label that's a third order, just so you remember. And it's as simple as that. There's your shear moment diagram. There's really nothing else more to it. Really, you can just look at what's happening with your loading up here and translate that down into shear and moment. But of course, if you had a hard time following that, you're just not really understanding how you look at it and you get it, that's okay. You can just go ahead and come in, cut the beam here, 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 and here. Develop your equations, and then just graph those equations to get your shear and moment diagrams. If you're having trouble with any of this, or you have any general homework questions, visit our homework help page. Or our tutoring page, and we'll be able to get you more specific help there. If you have any general questions, feel free to email us at taylorstutoring@gmail.com or use the chat function below.